All right, we'll start today's lecture. I have one announcement to make. I just received the information that this class is supposed to be 90 minutes. The reason is that this class is joint offer to the two universities in Japan, and their class is 90 minutes. And after 90 minutes, the teleconnection will be cut, so they won't be they won't be able to see anything or hear anything. So to be fair to them, we'll stop at the 90 minutes, and after that, I will be here. And if you have any question, and we can discuss. Okay, so we'll have a little bit advantage, not a tremendous advantage, over the Japanese class. Okay, all right. Having said that, because this is a joint offered course among us and the two universities in Japan, so we have to compromise about the schedule. And their schedule started October 1st and end in November, the end of November. It's 2 months. So I will try to concentrate all the material on HHT during that 2 months. Okay. So this week and the next week will be a prelude to discuss why I get into HHT. All right. So today will be my second lecture on why I'm doing that. And that, again, is another justification for my job in scalerometer. I told you I work for NASA for 30-some years. Why they hire me? For various reasons, because they want to use satellite to study Earth. And last time we discussed the altimeter or altimetry. And this time we'll discuss scalerometer. Scalerometer actually is the same radar as altimeter. In fact, the first scalerometer was flew on Skylab. Before we have satellite, there's a Skylab actually with people in it. And on the satellite, there is a radar. And this radar is hand-controlled, not automatic control, hand-control. So the ground will call the Skylab, says, okay, point your radar vertical. So then the astronauts will point the radar vertical. When you point the radar vertical, the radar will find the height. And it said, okay, now point it to the sideways. So when you point sideways, the angle is not vertical. So you still measure distance, but that distance is not your height anymore. And the scatter power coming back is totally different from vertical. So the same radar serves two purposes. Of course, later, the altimeter get more specialized, and they have changed design somehow to make the vertical measurement more precise. And scalerometer also changed some design to make the side looking more convenient. Yeah, but anyway, it's a side looking. Now, the measured parameter is the radar backscattering cross section or the intensity. So if you point radar at anything, you will have some signal bounce back to you. And the intensity of bouncing back depends upon the surface that the radar beam hit. For example, if you have a very glossy, very smooth surface, and then you have specular return. You point it to it, and then you return vertical. And you have a very rough surface, then of course the radar wave will be scattered, and the amount of energy you get back will be much less. So the scalerometer does not measure the distance. It only measures the strength of scattering. So the strength of scattering is proportional to the surface roughness. Okay. Now that surface roughness turns out is related to local wind stress. And wind stress is extremely important for an immediate application that's in meteorology. Yeah. In United States, I live on the East Coast in the state of Maryland. our weather forecast is very good. And they can forecast 5 days. And it's very precise. Sometimes they can stretch even 10 days. Why? Because they have all the weather data to the west of us. And the front always moves from west to east. So they know the condition as the weather front moves across the continent. What's the temperature? What's the humidity? Yeah, how fast the front will move, and what's the pressure change? Everything. So with that information, you put it in the computer, and all the weather system has certain inertia. It's not going to change from day to day or even couple of days. So you know what's coming, and so you can predict it very well. West Coast, however, the weather forecast, if you're lucky, you get 2 days or 3 days accuracy. Why we cannot get that? Because the weather front moves from the ocean. And in the ocean, there's no observation, no weather station. Yeah. The only thing you have is some IR, IR or visual. You can see the cloud pattern. But cloud pattern is not, it's not very good. It's related to precipitation, but it's not one-to-one. So why we need this? Because if in the whole world, as I said, more than 70% of the area is covered by ocean, and if we know the wind condition in the whole over everywhere in the ocean, then that will improve our weather forecast, our meteorological computation tremendously. So the meteorological community and even the oceanographic community really need the surface wind. And for the oceanographic community, it's even more strange. See, we in the oceanographic community, what do you need to know? We want to know the circulation, the current, how fast the current moves. And we want to know how high the wave will be. And all of this are closely related to our lives. For example, if we want to go out for boating, you want to know whether the sea will be very, very choppy or not. Okay, and if you have an accident in the ocean, and you want to know, especially these people who want to rescue you, they want to know what's the current condition, whether you will be drifted away from certain point or which direction most likely you will be drifting. So all of this, you need to know the current condition. How to compute the current? The oceanographer only know one way. Give me the wind stress. See, the current is driven by wind, mostly. So which direction wind is blowing? So that's how NASA sell to the communities. Is we're going to measure wind on the ocean everywhere. We're going to tell you not only the speed but also direction. Yeah. So the oceanographic and the meteorological communities really welcome these instruments. And these instruments, as I said, is side-looking. When the wave front hit here, it get a bounce back. Hit here, it get a bounce back. Hit here, it get bounce back. Everywhere you get incremental backscatter cross-section. So you can measure the wind here, measure wind here, measure wind here. So the spatial resolution is also very good. And if you averaged the global wind field, I'm sorry you cannot see this. This is really bad. You can see this line. This is actually backed out the wind contours. So you will be able to see how the global wind are over there. The red spot means high wind. The cold spot means low wind. So here, obviously, is a hurricane. Okay? So you get the wind field everywhere. Everywhere over the world. And if you look closer, you get a more detailed structure of the wind. And if you can even look even better, you can even look into the hurricane to see the wind structure. This is amazing because radar penetrates cloud. So Even if there's cloud, I can still measure wind. Yeah. This kind of picture make people really get excited. Say, wow, we want this. We want this. Always want this wind data. Now, how the altimeter can measure wind? Why a radar can measure wind? And that, I'm sorry, I have to use some Chinese. And then we have to go back to 903 to 960. This point, Feng Yanyi, yeah, is a he wrote a very famous poem. The very famous poem is 风乍起，吹奏一池春水. I think everybody knows this sentence. Yeah. And let me translate to some of you. The wind suddenly started and roughened the whole pond in the springtime, because winter time is so frozen, you cannot roughen the surface. Yeah. In the springtime, the wind suddenly started and the whole pond gets rough. Yeah. That's instability. The Chinese described this phenomenon in 903, but that doesn't count. It will take Kelvin Helmholtz to actually give the instability computation, and he actually compute the minimum wind speed that can roughen the surface. Yeah, that's quantitative. This is just a poetic description of what happened. But actually, the scalerometer is actually based on this. Yeah, and this poem is so famous that even the emperor get involved. The emperor, it's Li Yuan, Nantang Zongzu. Once talked to Feng Yanyi, said, the wind roughened the pond in the springtime. What's that has anything to do with you? The pond will be roughened. So what? Then he answered, says, well, you once wrote a poem. Says you blow the flute and make the jade cold. He says, well, whether the jade cold has anything to do with you? So this is the emperor and the his subordinate, the description of the situation. This is a very famous anecdote. To roughen the surface and to look on the side depends not only on how rough it is, but also depends upon how the backscatter will come back. And this backscatter come back depends upon the so-called Bragg scatter. Yeah, we'll talk about Bragg. Bragg scatter said only this kind of wavelength can get return backscatter. Without, if the wavelength is not this is a radar wavelength. The radar wavelength and the water wavelength will satisfy this condition. This is called the Bragg scatter. And why is that? If you have ocean surface, if I have radar beam comes like that. So when the radar beam first hit here, it starts to reflect. And when the radar beam keep going, when it hit here, it get to reflect. So this reflect and that reflect, if it's in phase, then you have a reinforced addition, resonance. Okay. This in phase resonance means that this wavelength and the angle, this angle multiplied by that has to be equal to exact one wavelength. And that's how this formula comes up. This is the Bragg scattering condition. Bragg is a very famous physicist, and he actually get Nobel Prize. Bragg did not study water wave. He studied something much more profound. And what he studied is use X-ray to look at the atomic structure. Yeah, this the so-called scattering crystallography. Yeah, just look at the crystals, how the crystal start, and the response is the same. The X-ray wavelength will have to be the equal distance that satisfy the so-called backscatter. And this work is so important that he eventually got his Nobel Prize. Bragg and his father get the Nobel Prize together. That's amazing, because his father is also a physicist, and he's a physicist. So they both working on this backscatter from crystal. And they first worked on very simple crystal, NaCl, table salt. Okay, he found the crystal structure of table salt, yeah, using X-ray and using the backscatter principle. And so when in 1915 he got his Nobel Prize, people always say, "Wow, this is." At that time, I think he's only 25. Yeah, and people always assume, "Oh, his father did the whole thing. And he just followed his father." Turns out, mostly it's actually his idea. Yeah, and later he becomes the director of Cavendish Laboratory at Cambridge University, and he's continually doing this X-ray backscatter, and from very simple crystal like salt, and eventually by the time of 1953, they are looking at the DNA. The DNA is very, very complicated structure, but you can still use X-ray to study it. At that time, many groups in the world were trying to solve the mystery of DNA, and Cavendish Laboratory is one of them. Yeah, and Cavendish Laboratory, they do not have a very good image of the DNA. Across the town in Imperial College, there was a young lady by the name of Rosalind Franklin. She painstakingly take many DNA crystal pictures, but she hasn't figured out what is the structure. She think it might be a helix, but why it is a helix, he hasn't figured out. Meanwhile, the Cavendish Laboratory were trying to using very crude image and try to build up a model, and the model was so bad that once they invited Rosalind Franklin to look at the model. And Rosalind Franklin immediately criticized the model, says this model is just totally wrong, and give lots of bad comments. And the comments so bad, so embarrassing, that Bragg told Watson and Crick, says, "Stop working on this. Okay, you don't know what you're doing. No more fooling around." Yeah. And meantime, in one of the visits that Watson went to the Imperial College, Maurice Wilkins is the director of the laboratory, took one of Rosalind Franklin's picture and showed it to Watson. And when Watson looked at that picture, it suddenly dawned to me, he says, "This is a helix." And then he knows enough chemistry and enough physics. They immediately figure out the double helix structure and published a paper in Nature, and the rest is history. But somehow a gross injustice happened during this incident, because Maurice Wilkins showed this picture to them, and they don't get the Nobel Prize, so they'll have to include him. But the picture is not his. The picture is Rosalind Franklin's picture. Yeah, but Rosalind didn't know. So they went to Rosalind and says, "Oh, you have done this work so well. Why don't you also write a paper? And the paper you wrote should say that, yeah, based on my work, my studies support a double helix structure." Okay, so Rosalind Franklin was flattered to be asked to write a full article in Nature. So she did, and that support Crick and Watson's conclusion. And they got the Nobel Prize. But by the time they get Nobel Prize in 1962, Rosalind Franklin has already died because she played with the X-ray without protection. Yeah, she, day in, day out, she was taking the long time exposure of the crystal of DNA, and she get leukemia and died. She never know what happened. Yeah, so Maurice Watkins get the Nobel Prize, not her. But the story is this: even if she lived, if she were alive during the time of the Nobel Prize, that would be a really big problem, because Nobel Prize will never give more than 3 persons. It's only 3, maximum 3. So then his lab director, whether she or her laboratory director should get Nobel Prize, will be a big fight, I guess. But after everything's over, Imperial College realized the injustice done to Rosalind Franklin. So Imperial College tried to do the right thing. They named the building that Rosalind Franklin worked as the Franklin Hall. Yeah, yeah. So if you go to Imperial College, look for that crumbled down building. It's named Franklin Hall. But anyway, this work is very, very important. Backscatter is very important too in study basic science. We oceanographers or NASA just borrow it for this very simple thing. Now, in order for us to know which wave part satisfies the backscatter, we have to know in the ocean how much energy is in that spectrum bandwidth. Because you measure the whole ocean is a whole spectrum. And the whole spectrum, which part is important to the backscatter? Yeah. So we need to know the spectrum, the whole spectrum. Not only once we know the whole spectrum, then we'll be able to narrow down to that particular range. Okay. So looking for ocean wave spectrum becomes important to NASA by that time. But of course, long before that, wave spectrum is important for many other applications. We want to know how the wave component interact with each other. We want to know the air-sea momentum energy flux. You also want to know which part of the wave actually receive energy from the atmosphere. And you want to know the probability study of the ocean wave, like what we discussed the last time. And the probability discussion, many of the expression depends upon the moments of the spectrum. So we need to know that. And you want to design a vessel, a ship. You need to know the spectrum because you want to know the typical wavelength. You don't want to design the ship right at exactly one wavelength, so half wavelength. So your ship is always going up and down, going up and down. It would be so rocky. Okay. Platform, oil platform, of course. All kinds of marine structures. You want to know the spectrum because you want to know you want to put your structure member that will receive force not at the exact one wavelength. If you get exact one wavelength, you are inviting Bragg resonance. Yeah. So every wave, every peer get the same amount of force. So the resonance will actually increase the force to your structure tremendously. So to know the wave spectrum has been a very long sought after goal. And but the history developed slowly. At the beginning, people want to know. We look at the wave looks random. how can we describe this? So people say, well, if you have a spectrum, you know statistics of the wavelength or frequency distribution. Yeah. But at the beginning, we don't have actual data. And we don't have computer resources to make the computation of the wave spectrum. And so, the early people, we don't have the computer resource. Why we don't have the computer resource? A, the computer is not very fast. B, is that the Fourier transformation is not that fast until 1965. By 1965, Cooley and Tukey invented the FFT, the fast Fourier transformation. Before that, Fourier transformation is not fast at all. It's very, very slow. Painstakingly take one transformation after another. Anyway, so without the data, without the computer, you don't know what the spectrum looks like. So people just guess. Just, well, the spectrum probably looks like this. And the guess was so bad that even the dimension were wrong. You know the dimension analysis, do you? Dimension, like velocity, is L over T. Is length divided by time. So that's dimension. So in physics, every equation should have the same dimension. Okay. For spectrum should have certain dimension. In this case, it's L squared times T. So when you integrate with frequency 1 over T, you get L squared. So that's the energy. So even the dimension were wrong, but people don't care. Even today's day, the ship testing association, the worldwide organization to design ship, boat, and their testing spectrum is based on a spectrum that has a wrong dimension. Well, people still use it, empirical kind of formula, so they don't care. They still use that. So until 1958, Phillips published a paper. Phillips was my advisor at Hopkins, and he is one of the pioneers in wave study. In 1958, he was inspired by Kolmogorov, a great statistician and physicist and mathematician from Russia. And he studied, Kolmogorov studied the turbulence. And he found that the turbulence spectrum should have a uniform form. And this uniform form he derived from dimensional analysis. He says, well, because of the dimension of the spectrum should be L squared times T, so what kind of length scale is important? What kind of time scale is important? And if you put it all that together, then the spectrum shape should have this asymptotic form like that. And when Phillips read that paper, he said, well, let's use that for let's use that to study wave. So he, in 1958, he published one of his famous paper on spectrum. I will discuss his form, but I will also mention, however, in 1985 he changed his mind. Okay, let's first look at what he first initially proposed. Initially, he proposed the following. He said that spectrum, the asymptotic form of the spectrum, should have a very, very simple form, like a constant times g squared over n to the fifth. That's it. Yeah. Why g and n? He said that the spectrum, especially the high frequency part of the spectrum, should be limited by the amount of energy that the wave can contain. And if you put in more energy, the wave will break. Yeah, you cannot push wave unlimited high because the wave will break, like rollover. Like you look at the some of the dramatic picture when people doing surfing, is the wave rolling back because the wave cannot grow high any higher. Yeah, the wave will have to tumble over. So what dictated the tumbling over? the tumbling over is dictated by gravitation. If there's no gravitation, the wave will never tumble down. The wave will just keep growing. So gravitational force is important. What's the next important thing? The wavelength. Yeah, how long the wave is. See, if I have a very, very long wave, and so even a very gentle wave, I can still exist. But that gentle wave is infinitely long, then the wave can still be high, like a tidal wave. The wavelength is almost a half a basin. So the height of a few meters doesn't even show. Yeah. But in water wave, the wavelength is related to the frequency, is related to the phase velocity, is related to everything. Okay? So once you know the wavelength, you know the frequency, you know the propagation speed. This is called the dispersion. Water wave is a few wave phenomenon, has dispersive property. Dispersive property means different wavelength or different frequency wave propagate at different speed. Yeah. In water wave, for example, if we have a hurricane out in the open ocean, on land, you first see very large wave coming out. Swell first come in. And the swell can propagate so far that at California, you can measure the storm in southern Indian Ocean. That wave will coming gradually to California. But how about the shorter wave? The shorter wave, if it does not dissipate, it should arrive later. It will take years to get there. But long before it reaches there, the energy dissipates. It's all gone. Now, light wave is not dispersive. Light, the white light, has rainbow color. And they all arrive at the same time. That's why we see it's white. And if light wave is dispersive, then we should see different color come first. The long wave come first. The red wave should come first, and then eventually the purple. Yeah, it doesn't work that way. Light wave, all the waves propagate the same speed. Water wave is not. Yeah, and that is one of the advantage we have in water wave study. So, because this frequency is related to wavelength, related to propagation speed, related to determine the whole property of the wave, kinematic of the wave. So Phillips said that the G and N G and the frequency should determine the spectrum shape. And the frequency is 1 over T. So if you put this together with B as a non-dimensional constant, you should have a spectrum like form like this. And if you look at the spectrum measured, then you draw a -5. This is frequency. You draw a -5 line. You see how parallel it is? It's very nice. Yeah. So that is the asymptotic form of the spectrum. So Phillips was right. Yeah. And after he published this very short paper, actually, it's one of the shorter papers that he published. And so many people come out and say, yeah, I see -5, and I see -5. Everybody see -5. And if you see the slope -4.5, your paper won't be published. Because people say, well, go back and check your instruments. Okay, why you didn't see -5? The theory says -5. Yeah. And this -5 becomes so dominating, and for years, all the papers say frequency is -5. But this -5, however, is open-ended. And when you come to the lower frequency, you don't know how they turn around like this. So this spectrum shape is open-end spectrum shape. Then in 1962, Kitagrodsky, a Russian scientist, posed an exponential term to bring the spectrum back down. So this is called Kitagrodsky spectrum. But in the United States, it's not known as Kitagrodsky spectrum. It's known as Pearson-Moskowitz spectrum. Yeah. Anyway, so the spectrum suddenly added a exponential term. This exponential term has no a priori, no physical justification. It's just a nice and fast decay curve coming back down. Yeah. So now we have a spectrum shaped like this, and the spectrum will look like this. This Pearson-Moscovitch spectrum looks like that. But then people start to go out and measure more and more spectrum, and they find the spectrum actually depends upon the fetch, how far you're from the coast. The spectrum looks like this, and when you fit, for example, this spectrum, you find the peak is much higher than the Pearson-Moscovitch spectrum. Pearson-Moscovitch spectrum is a saturated wave, but when the wave is under development, it doesn't fit that form. So because of that, this famous person, Hasselmann, come up with a gruesome addition. He added a peak enhancement factor, and peak enhancement factor has this ugly form. Yeah. So in one swap, he added 3 more parameters and make the spectrum almost like a total curve fitting. Yeah. How wide the spectrum is, how high it is, and all that. But Hasselmann is such a famous person. He is the chairman of Max Planck Institute of Meteorology at Hamburg in Germany. And I was told that he was even nominated for Nobel Prize once because of his various work in the nature phenomenon like a wave interactions and all that. But of course he didn't get it. But even the fact that he's been nominated is a big honor. Now because he proposed this, the proposed is based on some measurements in the off German coast. It's a very short fetch. So he measured this spectrum based on those data that I showed you previously. He proposed this form. Everybody followed him. He said, "Oh yeah, the spectrum looks like this." And not only look like that, asymptotically it looks like Phillips. Phillips is a big name. So if you have a spectrum that fit both Phillips' description and Hasselmann's model, you cannot go wrong. Anybody want to find an argument with you, you can say, you go argue with Phillips or Hasselmann. So people keep publishing paper based on this basic form. But when I look at the spectrum, I find something very different. Yeah. So when I look at the spectrum, this is one of the spectra that here. If you look at here, there are many different spectra. Some spectrum look like this, some spectrum look like this. Okay. So if I look at each individual spectrum, the spectra are very different. The spectrum looks actually like this. Now, I start to draw a line to go close to the spectrum, not just an asymptotic shape of all the ensemble of spectrum. I want to look at each individual spectrum, how this individual spectrum looks like. The individual spectrum looks like this. So I can draw a line like this. Other people may have idea of different fitting. So it becomes very difficult for people to say, if I give you the spectrum, everybody draw the same line. It's very difficult. Different people can draw different lines. So I said, look, instead of let everybody draw different lines, I will use the peak of the spectrum, which everybody can identify. I will use the secondary peak, which also everybody can identify. If I draw a line between this peak and the secondary peak, and that will form a line, and that line everybody will draw the same. And is that line a good asymptotic shape? It turns out from the picture it looks pretty good. But I will later show you how other people draw their lines. Now I say if people draw a line from here to here and draw a line that will be a good asymptotic fit, then the relationship between this point and this point can be calculated theoretically. Why? Again, we go back to to the wave, fundamental wave theory. The connection between the peak and the peak of second harmonics. It turns out this second peak is exactly twice the frequency. Yeah, that's the second harmonic. In Fourier analysis, you cannot avoid harmonics. So you draw this line, you actually draw the primary wave with its harmonics. Yeah. And this harmonics seems to fit a good overall asymptotic. In this case, the slope can be determined. And how to determine that? We come back to this formula again. According to Stokes, who derived the water wave, and we talked about the water wave the last time, I show you the water wave cannot have a round-off tip and sharp trough. Instead, the water wave all has a very sharp peak and round-off trough. The valley, the trough, is more smooth than the crest. So the water wave is nonlinear, is asymmetric. And what nonlinear cause, how the cause that the sharp crest actually is the harmonics. Yeah. We don't have a whiteboard, otherwise I would draw you a picture. But other people won't be able to see it, right? Sorry for them. Oh. Okay. Okay. This is this is as good a sine wave as I can draw, cosine omega t. And the second harmonics will be the twice the frequency. Okay? This twice the frequency. So if I add these two together, what do? I add here positive, here positive, here negative. So I will draw another wave like this. So now you see the peak get sharper and trough gets smoother. That's how the second harmonics come in forming the very sharp crest. And this is only two terms. Actually, oh, very nice. Actually, people doing this harmonics, they have gone to 120. The last time I read a paper some 20 years ago, somebody went to 126 terms of this expansion, and you indeed get a very sharp crest and a very round off trough. Yeah, but after that, nobody care about going to 300 terms because you already proved the point. Yeah, in fact, you can prove the point with two terms already. With two terms, you prove the point. It says, okay, this harmonics indeed can give us. Whoops! What happened to the? Oh, oh, so you have control. Very good. The harmonics already give you the amplitude, the peak amplitude change. Now, if the harmonics is indeed described by this famous Stokes wave. Stokes is a very good mathematician. He's the inventor of Stokes theory, the triple integral, I think. Yeah. Stokes, if the wave is Stokes, like Stokes, the primary peak is A. The secondary peak is A times, oh, I'm sorry, this square should be here. Change it, okay. It's A squared K, not AK squared, sorry. It's A squared K. Should be A times AK. Then it's A times the slope. AK is the slope. Slopes usually small. So this peak is much, much smaller than that. Now, if the primary peak is given by A times cosine chi, when we discuss probability, we say if A is really distributed, chi is uniform, we'll Gaussian distribution. And if you add this, we get a non-Gaussian distribution. Now come to the wave. The peak is actually A squared, is the energy. And the second harmonic is this term squared. So the difference of this minus the base, the difference, should give us that slope. And that slope is determined analytically. And that analytical description can be written in this form. Yeah, that's very simple algebra. And once you've written in that form, then you can write this, because it's very difficult to measure A, amplitude. So what you measure is the elevation of surface height. The surface height for a sine wave is A over square root 2, and K is 2 pi over lambda. So you reduce these two terms together, you actually get one parameter called the zeta square, root mean square of surface elevation, divided by the peak wavelength. That gives you a slope. And that slope I call the significant slope. It's the representative slope of the wave. Yeah. And in terms of that, the slope equals to square root 2 pi times s square divided by square root 2, log 2. And this simple formula need to be verified. So I measure all the spectrum slope, and indeed I find a gradual change. And this is the theoretical prediction. Yeah. So it looks pretty good. Now, armed with that information, then I want to see if slope equals to that, then I proposed a different spectrum. So instead of -5, now my slope is not 5. My slope should be m. But then how you write this m into that? So I decide use the previous form. The previous form is beta g squared over n5. That I don't want to touch. But I change this n into a constant n, which is the peak frequency. Yeah. Then I multiply that with n0 over n. That's the peak frequency over with whatever the variable frequency, and raised to the m. So this is the variable, and the slope is determined by that. So then my slope is indeed changing with m rather than rather than stay with -5. Okay, and I borrow this part as previous people use, but I use this delta and eta. So I have beta, m, which is already known, delta and eta. I have lots of constants, but these constants are not free. So we can determine this constant by the property of the spectrum. And one of the ways, so we want to determine beta, delta, and eta is to be determined. And one of the things that we know, at the peak of the spectrum, the derivative of the spectrum has to be 0. That's the maximum. So if you take a derivative of the spectrum, set it equal to 0 at n equal to n naught, you find that the m equals to the delta times eta. The delta and eta multiplication has to be m. And that's a constraint. So now, if we this is still a underdetermined system. So if you choose eta equal to 4, like what other people, then delta equal to 4 over m. So now you have everything determined. And not only that, this beta can be also determined by, say, phi eta, phi integral of the spectrum equal to RMS wave height, the mean root mean square. If you integrate that, the only thing you don't know is beta. And you solve that, you find the beta equal to this formula. And this formula this is a gamma function, and m is whatever the parameter that we have already calculated. So this spectrum has no free parameters anymore. If you know m, then you know the spectrum. But what is m? M is determined by the steepness of wave. So if you know the steepness of wave, you know the spectrum. That is what the spectrum that I propose, I call the Wallops spectrum. Because at that time, I work at the Wallops. So I used place name to propose that as a spectrum name. And I was much more modest then. I was a young man in my 30s, so I used the location name as the spectrum. And later when I did the HHT, I was a little bit old and my skin get a little bit thicker. So when NASA people suggest Hubert Huang, I did not resist too much. Anyway, so we get a beta form too. And this Wallop spectrum give a smooth spectrum. The only two things I have to know is this this n and a steepness of the wave. And once you make a comparison, I will come back to that. And then now I plot the beta with the steepness, and it looks good like before. Okay, and so once I find this good, then I decide to compare with other people's beta. Because if you find a formula, you really don't want to just compare with your laboratory data. You want to compare with everybody's data. And when I compare with everybody's data, I was shocked. The black dots are my data. The first group here is the first group I got of the beta that I showed you in previous graph. Then once I plot everybody's data, it looks like this: one cluster, another cluster. This parameter, however, is g times x over u squared. Gx times u squared. Gx u squared is one of the parameters that most oceanographers use. X is the fetch. When your wind blow from the coast, at a pond, for example, you blow wind. Near you, the wave will be very small, and the wave will gradually grow bigger and bigger. Yeah, this is an everyday phenomenon, and that is of critical importance, not only to wave, but also to my thought of thinking HHT. Yeah, the wave will grow. So how to describe the wave? A very natural parameter is the fetch, but fetch is dimensional, so we make it non-dimensional. We time a g divided by velocity, wind velocity squared. So this is called a non-dimensional fetch. People like that. Everybody use that. Okay. So in the past, when people go out in the field, that fetch is very long. The field fetch is very long, kilometers, hundreds of kilometers from the coast. Okay. So their fetch is 10 to the this 5, 6, 7, 8. Their fetch is over here. I'm in the laboratory. The laboratory fetch is a few tens of meters, 20 meters, my laboratory. So my laboratory is over here, 10 to the 2. And the field is 10 to the 7. Yeah. So this cluster of data here, that cluster of data sit over there. Most people in the field, in wave research, was not bothered by this, because they look at this, they draw a big black line that connect the two. Says, okay, look, it's a function of fetch. Yeah, and indeed that was done. Yeah, draw a big line over here. They went through the cluster pretty good. But when I get this, I said, well, look, my formula is not a function of fetch. My formula is a function of steepness. Now, how can I fill the gap here for this intermediate gap? This gap has very, very different fetch. The fetch is much longer than most people's wave tank, but it's much shorter than the field, say a few tenths of meters. I only have 20 meters. How about 50 meters? Nobody has a 50-meter tank at that time, wind tank, okay, or 100 meters. Nobody has that. So, so there's absolutely no data. And when you go 50 meters in the field, you barely get into the water. So how to fill this gap? I come up with a scheme. In my tank, I've shown you the tank the last time. My tank is about 20 meters long. I generate a wave, and I record the wave at the end of the tank. And I take that signal, I play it to the plunger. So the plunger will move according to the wave to create the wave condition at the end of the tank. So it propagate, I blow the same wind, then I record that wave again, and I bring it back to the beginning. So by doing this 3-4 times, I can increase my tank length 3 times, 4 times, 5 times. Yeah. So by that, I was able to extend my fetch. By extending the fetch, I keep getting data. And I was expecting the data to connect to this, but my data doesn't follow my order. It actually doesn't follow my wish. The data actually comes down like this. I was shocked. I said, well, gee, this is no good. Then that means this fetch parameter cannot be true. If it's true, all this data should go the other way. So with that, I said, well, if the fetch parameter is not true, how about to try the parameter that I come up with? I replot the data as function of steepness. Then the two groups of data, the previous experiment and the field, all clustered together. Not only is all clustered together, my data also clustered together. And this is the theoretical curve. Yeah. So that's amazing. For a long time, people think that the beta is a non-dimensional constant. Yeah. And everybody's arguing the constant should be 10 to the minus 2 or 3 times 10 to the minus 2 or 4 times 10 to the minus 2, even though the difference is not big. But if you change your beta, you linearly change your energy content of the spectrum. So people are trying to argue what the beta should be. And turns out the beta should not be a constant. It's a non-dimensional function of wave steepness. Yeah. And at that time, this is around 1980 or something. At that time, Phillips is already very famous. And if you come up with anything says, well, beta is not a constant, that's tough because Phillips says it's constant. So I sheepishly went to Hopkins and saw him, and I showed him the result. I said, look, I get this. Well, before that, actually, I tried to get the paper published. The reviewer come back with a very simple comment. So if this is wrong, we all know beta is constant. And you go through this simple computation and you try to convince me that you're right and everybody's wrong. I mean, your computation is so simple. So we cannot accept this paper and give it reject. Send it back. I was so frustrated. I wrote back to the editor, who's also my friend. I said, simple, you use this word simple, I think it's very interesting. Simple doesn't imply trivial, doesn't imply wrong. Okay. If everybody knows Newton's law, F equals ma. Everybody knows that, right? That's Newton's law. And even after you learn a little bit of physics, you know F equals to ma. But what if I write F minus ma equals to 0? Is that
yes. We cannot hear you.
Hello?
Excuse us, we cannot hear you.
Oh. Okay, repeat.
Excuse us again. We cannot hear you.
Wait. Hello.
Yeah. This is good. This is good.
Somehow the mic
Yeah.
drift and drop off. I was recounting a story, my personal story, my personal experience. I wrote a paper describing beta like this, and the paper was rejected. And the reviewers' comments say that everybody knows beta is constant. And now you come up with this simple formula and you try to convince us beta is not a constant. And this formula is trivial and it's wrong. Yeah. So I wrote back to the editor, whom I happen to know. I said, look, simple and trivial does not equal. Yeah. I used the example of Newton's law. Newton's law says F equals to ma. Everybody know that. And if you go a little bit beyond 7th grade, I think you learn enough algebra. You can write F minus ma equal to 0. And that's identical to Newton's law. But F equal to ma, F minus ma has a new name. Anybody know this new name? D'Alembert's law. A very famous French philosopher, physicist, mathematician. Yeah, he said that look, the sum of the force is equal to 0. Okay, instead of F equal to ma, the sum of force is equal to 0. I said because of that, you cannot simply write off my comments. Say that my result is beta is not a constant based on the simple derivation. My derivation is so simple. Since they won't publish my paper, so I have to go to Professor Phillips. So I went to Professor Phillips. I showed him the result. I said, listen, I'm sorry that now I don't believe beta is constant. And I tried to get my paper published, and nobody will publish it. They think it's trivial. And I showed Professor Phillips what happened. And Professor Phillips was shocked to find that such a simple rule can actually actually govern the beta. So instead of a oceanographic journal that I originally submitted, Professor Phillips took this paper and published it in Journal of Fluid Mechanics. Yeah. That journal, in my mind, is a much better journal. Journal of Fluid Mechanics is published by Cambridge University Press. And this brought another side comment. Many people try to measure paper by the journal they published. Journal has to be SCI to begin with. And even SCI, you have to have high impact factor. Okay. GFM happen to have a very low impact factor because not many people read it. But the paper in there are of much higher quality than most of the oceanographic journals. Because I have been editors of JGR and JPO, I know the quality of the papers. Yeah, they're way below Journal of Fluid Mechanics. Yeah. Anyway, so now we can relate beta with a simple parameter S. Yeah, and I think that is a very interesting study. Now, once we find that, then I ask myself, says, if this significant slope has such a wonderful property of parameterize the Phillips constant, beta. Now it's not constant anymore, Phillips coefficient. Yeah. Can it be used for other applications? So I start to look for other applications. The other application is, of course, I go to the John-Swab spectrum. Remember, John-Swab spectrum has lots of parameters. This gamma, which parameterize this, and gamma has alpha, which is both the thickness and everything of the shape of the spectrum. And again, this alpha is nothing but Phillips constant. Okay, So, however, if you go back to look at the John-Swap spectrum, they also present their data in terms of the non-dimensional fetch, which is gx over u square, velocity square. Yeah, and it plot like this. When you look at this, you say, well, we have a very large scatter, but then it starts to coming down. So maybe that's the truth. Yeah, maybe it's true. Yeah. This kind of scattered diagram, when we take it over and replot it another way, which is u star over c. U star is the wind velocity, c is the phase velocity. And u star over c in wave study has another name. This is called the non-dimensional age of the wave. Why it's called the non-dimensional age? The phase velocity will increase, getting bigger and bigger. So getting bigger and bigger, that means the wave, as the wave get longer, it will propagate faster. So under the same wind, this ratio will decrease. So these are very old wave, these are very young wave. So the explanation is that the young waves is a lot unruly, just like young people don't follow rules. But once you get old, then they start to settle down in a rule. Yeah. So when people get this kind of data, they are very happy. They publish this kind of graph everywhere, and it's widely accepted. And when I get this, I decide to take their data and a lot of more data, plotted as a steepness. Instead of young and old, scatter and not scatter, they all follow the same line. Yeah. So that shows that this significant slope is a controlling parameter in wave study. Now we have to know that all of this I'm driving to nonlinear phenomena. Yeah. Nonlinear immediately govern the whole beta. Not only beta, we can look at other thing. Gamma. Gamma is the most difficult parameters to write a function of. So gamma is how high the peak will grow. And if you collect all the John-Swap data, you find that you plot as wave age, it look like this scatter. Yeah. This is another incident. Actually, it's precisely this paper. 4 people from 3 countries submitted a paper to me. At that time, I was the editor of JGR. Claim that this gamma, getting this data, they can draw a line through it. Okay. And these 4 people come from 2 from Germany, 1 from France, 1 from Italy. Yeah. Some to JGR to me. I sent out for 2 famous people for review. One is Vela Pearson, a professor at the New York University. Other one is Professor Kitagroski at the Johns Hopkins. He used to be at the Russia Academy, but he left Russia and come to the United States at Johns Hopkins. I sent them for review. Through this data to draw a straight line. And both of them recommend to publish. This paper is so good that it has lots of data, and you can sort of getting a line roughly length through this. Of course, there's some scatter, but usually you can find a line here. When I look at that paper and I look at the review, I reject the paper. And I send both referee report back to them. These four authors get so mad at me, and they wrote back, just listen, look at the reviewer's report. Both say that it can be published. How can you reject my paper? I said, look, I'm the editor. Okay, they are not. They are reviewer. They offer their help to me. I think their comments is useless. I cannot see a line. Of course, at that time, I haven't got anything better, but I cannot see a line. So I say I cannot accept it. But they get so mad. So the four get their paper published in the famous German paper, German journal, which is SCI too. Yeah. After that, I went through the data, and I plot that parameter as a function of steepness. I get much better result. So the steepness, the peak enhancement is not a function of fetch. It's not a function of wave age. It's also a function of nonlinear phenomena. Yeah. Now, armed with this and the other result, I went to Hamburg to show this result to them. Use the Taiwan local dialect as just 踢馆. Yeah. I went over there and showed them this result. They have nothing to say. Yeah. We cannot use any data, just draw lines through it. And unfortunately, the data processing people nowadays still doing that. Just try to draw straight lines. I used to make fun, but that's overhead projector. Now I lost all the overhead projector. So I find that too bulky to carry. I used to have an example, and that example is I made many set of that example. There's all the example. After I made the presentation, people asked for that, and they took it away. Yeah, it's precisely this kind of data, how to draw a straight line through it. Okay. People draw a straight line through that, and I cannot accept that. It gives me such a cringe that I just cannot stand it. So I made a joke. I put a constellation chart, the stars. I plot the star position. Okay, it's scattered just like this. And the star part I got is the Ursa Major, 大行星, Ursa Major. Yeah, it's scattered all over the place. And I say, well, what kind of line should I? And based on this, I should draw this line or that line or that line, or whichever famous people draw a line will usually stick longer. Yeah. I say, what kind of line you suggest for this? Because nobody makes suggestion. I said, I will tell you the most famous fitting of this scatter chart. Actually, the most famous fitting is a bear. You draw a bear through that. You have head, you have paw. You have I said that this bear, you know how long this curve fitting stands? Thousands of years. Nobody's curve fitting stand that long. Yeah. Once you get data, try to think. This is some of the philosophy I try to impart to you. Don't just draw a straight line. Draw a straight line is the easiest thing. Yeah. You look this way, you look that way. When you get tired, you'll find a line. You just draw. Yeah. But if you actually examine the data, examine the physics, examine the mathematics principle, you will eventually find a much better way. Then draw a straight line. And that line, if that line is right, usually make a lot more sense. And another thing is, don't overlook the simple solution. By simple solution, I don't mean straight line. Simple solution with physics understanding. And once you find that find the right physics is always the most simple physics. It's not going to be complicated. It's not going to fill the page with all equations. Yeah. This is one of the illustrations that even before I get into HHT, that's my way of doing science. Okay. Conclusion. Yeah. Apparently, the spectrum shape is not that complicated. Yeah. It's not as complicated as Hasselmann said. I have to introduce 5 parameters to describe just one spectrum. Turns out that with the Wallop spectrum, I feed data better than Hasselmann's spectrum every time. Yeah. This two parameter model works well. Yeah. That works well for the energy containing range. Yeah. Future study, however, should try to establish the parameter exterior parameter to interior. The parameter that I use is the steepness of the wave. Steepness of the wave is the property of the wave itself. So if you look at the wave, you know the steepness, you can immediately draw the spectrum. Yeah. But that steepness is not a function of environment. And then this is a philosophical question. Should the steepness be a function of environment, like wave age, fetch? Should it be that function? I contend it should not be. Why I contend it should not be? I can see a rough patch of wave anywhere. Yeah. The simplest, easiest place is at the mouth of a harbor. Yeah, entrance of a harbor. Entrance of a harbor usually have current, because tide wave brought water in the harbor, and at ebb tide, water try to flow out, and the wave always come in. So when we have wave against each other, the wave will get much rougher. It has nothing to do with fetch. It has nothing to do with wave age. Yeah. So the interior parameter is more physical parameter than the exterior parameter. Now, after this, I have to come back to tell you another story. I told you when Phillips first published his -5, everybody's spectrum is -5. Okay, if you get -4.5 or 5.5, that will not get accepted. But meantime, in 1973, Professor Yoshiaki Toba, Toba is a professor at Tohoku University in Sendai. He used to be the president of Japanese Oceanographic Society. Yeah, he's a very nice gentleman, very good friend of mine. Yeah. Yoshiaki Toba proposed a spectrum. He said that if we use dimension, I don't have to go -5. Say, you say G is important, I agree. Gravity is important. Okay. Frequency is important, I agree. Frequency is important. How about wind? He said. That if I put wind in, then I have G times wind. That gives me L squared. The N5, I drop that to 4, -4. So he proposed this in 1975. Nobody looked at his spectrum. Yeah, because every United States in English-speaking English language journal dominates the scientific community. Nobody studied. Nobody pay attention to this, except NASA. At the beginning, I was talking about. I said, we want to use scalerometer. We have to tie back to scalerometer. Scalerometer say that by looking outside, I look at a patch of wave. This wavelength has to match up with my radar wavelength. How long is the radar wavelength? Radar wavelength is in centimeter range. Yeah, it's 13 gigahertz. It's come about 3 centimeters. Yeah. So the wavelength that match up with that is about 4 or 5 centimeters. 4 or 5 centimeters wave. It's very short, and that wind generated that immediately. And once wind stops, it dissipates immediately. So this wind is very local. Why we not measure wind with long wave? Because long wave persists too long. You can blow wind here, the long wave propagate across the ocean like a swell. So long wave is the indication of history of wave at somewhere, but not wind condition here. If you want to determine the wind condition at that location, you have to go back to the 10th century to follow the Chinese point. Yeah, say that the wind roughened the surface right here. Yeah. So you look at the small range, you look at that range, that will be a function of wind. This NASA try to push scalerometer. So scalerometer will measure wind because the roughness should be a function of wind. If you look at the Phillips range, Phillips spectrum, Phillips spectrum is constant. The wind is not there. So based on Phillips, you should not be able to see wind. So even though Phillips is a very famous oceanographer or wave pioneer, but if you predict the wave is not a function of wind, if NASA try to use the spectrum to measure wind, so there's a big conflict. So immediately they say, well, we have to go to TOBA. So by the early 80s, people start to pay attention to TOBA's work. So dug TOBA's paper out and find that the spectrum strength at a given frequency indeed is a function of wind. Yeah. But given frequency and given wavelength is two different things. Yeah. I told you the wave should be dispersive. Yeah. But when you go to this range, high range, it's certain centimeters, this is already non-dispersive. So people say, well, forget it. Anyway, it's a function of wind. Yeah. The velocity should, the spectral intensity should be a function of wind. Now, having said that, let's look at how TOBA got his spectrum shape, how he determined that should be a function of wind. This is the spectrum. And TOBA's tank is even better than mine, or perhaps better than mine. Look, he got he got the peak, second harmonics, third harmonics, fifth, fourth harmonics. You get all kinds of harmonics in his spectrum. Okay? Now, how did he draw the line? He drew the line here. He went through the dense cluster of data. Okay. What he neglected here and here. Yeah. And is that reasonable? But that's how he determined it. Yeah. That's how he determined it. This part is indeed a function of wind. But to use that as an asymptotic shape of the spectrum, you have to be very careful. What you neglect is this line, cut this off. Now, remember, this is log scale. What you cut off from here to here is more than a decade, 1 to 10. If you plot this spectrum in the linear scale, what he fit is right near the zero line. Yeah. So this is the tail. This has 1, 2, 3, 4 decades below zero, below the peak. It's tiny. It has absolutely no energy at all. Yeah. Using this part as a parameter for spectrum is very difficult. However, TOBA spectrum has its use. That is, he said that if I concentrate in this range, and I keep on drawing a straight line, and that part grow linearly with wind. And that's how NASA claimed scalerometer should work. And NASA, instead of, once he found that, NASA said, forget about this spectrum shape, I don't care, as long as I have something grow with wind. And, and they also say, forget about the spectrum shape. I don't even want to know the spectrum shape. I don't want to know anything. I just flow my scalerometer, measure the backscatter, measure the wind, and plot a empirical relationship. So the algorithm NASA eventually developed is totally empirical. Yeah. And that empirical result goes through all kinds of detailed dynamics, draw a big broad straight line of wind increase linearly as a spectrum intensity. That's what NASA did, and that's what the wind velocity field that you see over the world is determined from. And there are a lot of interesting problems buried in there. And that's very different from the line that I draw. Yeah. The line that I draw keep the peak, but the TOBA's line is very different. Yeah. Now, whatever the spectrum it may be, it's not usable for NASA. So NASA said, well, forget it. I don't want to know the spectrum shape anymore. So for a long time, I justified my position. So I'm looking for spectral shape, and that gave me about 10 years almost to study the water wave. And later say, well, forget it. I don't need a spectral shape. I use empirical formula. Yeah. And so meanwhile, my problem with traditional spectral analysis becomes increasingly irresolvable. I cannot tolerate the traditional approach anymore. Why I cannot tolerate traditional approach? Because the traditional approach actually use Fourier spectrum, and the Fourier is a linear method, and through all the study, from probability, from spectrum shape, everything indicates the water wave is not linear. And if water wave is not linear, why should I keep on doing this? So then I decide I have to go a different way. But that, by this time, I have not totally give up yet. Next time, I will describe the breaking point. I totally break with the linear theory. Okay, so with that, we will end this class because we'll now try to get into a pattern. 90 minutes will stop because the Japanese will cut off at 90 minutes. Okay, so I will stop here, and I will be here for at least another 10 minutes for you people to ask a question, to have a discussion. All right. So and also next Tuesday we will not meet. We'll skip next Tuesday. Next Thursday. Wednesday. Next Wednesday. I'm sorry. Next Wednesday we have no class. You get a day off. We'll meet Friday. Okay. All right. So any questions? Since the Japanese is not here yet, we'll relax the rule a little bit. You can ask a question in Chinese. I will try to answer it in English. Okay. 有没有问题?
Okay. Excuse me. I want to ask a question.
Oh yes. Go ahead.
So you say that the water wave is a sort of dispersive wave, right?
Yes.
So do you mean that in general we have enough like knowledge to classify, for instance, if we
Just
have
one
a water
moment,
wave,
I cannot hear you.
Okay, sorry. So do you mean that if we know like a wavelength, then we know speed, we know everything?
Sorry, it's too noisy. I cannot hear you. Could you repeat your question, please?
Okay. My question is that you said water wave is a sort of dispersive wave, and you say that if we know the wavelength, we can know everything about the water wave. So is there a specific formula?
Oh yeah, water wave is dispersive, and the specific formula is sigma square equal to GK plus gamma K cube. Sigma
can you repeat it again?
Let me write it down. Yeah. I should have a view graph for that. I thought of that last night, but then I thought that n squared equal to GK plus gamma K cube. G is gravitational acceleration. Gamma is the surface tension, kinematic surface tension parameters. Okay, so if for large wave, for very long wave, the K is so small, so then the surface tension is not important. So we have n squared equal to GK. Now, since you get n squared equal to GK, then you can follow this by other once you related frequency, is a frequency divided by k equal to the phase velocity. Yeah. So with this formula, you can immediately divide this by everything by k squared. Then you will get a velocity square equal to whatever, equal to square root of g over k plus gamma k. Yeah. So that's the formula. And once you know this, then you know the relative relationship between n and k. You can perform a derivative with respect to frequency, and you get the group velocity too. So indeed, we have once we know the dispersive relationship, we know a lot about the kinematic property of the water wave. Yeah. Did you get that?
And, yes.
Okay.
Thank you.
Sure.
It's clear.
Yeah.
And in class, you also mentioned that in some range, water wave is not a dispersive wave. So does that mean that when we apply this formula, there should be a range of the frequency?
Oh, yes. Water wave is always dispersive. And however, if you look at the spectrum, even the spectrum I draw, here's the peak, here's the harmonics. Okay? This harmonics and this peak is propagating at the given phase velocity. This frequency harmonics, the harmonics is, this is frequency. The harmonics is twice its frequency. Should it follow this formula? The answer is no. Because harmonics has to propagate at the same speed as the peak. If not, your waveform will be distorted. So water wave is dispersive, but in the spectrum, only near the peak has dispersive property. The rest of the wave is not dispersive. The rest of the wave is not a free wave. And that's why I do not like Fourier spectrum. The Fourier spectrum lump harmonics, the free wave, and the bounded wave together. The harmonics are bounded wave. They are not free waves. So once I give you a spectrum, you don't know whether the spectrum are all free wave or part of the spectrum is bounded wave. And all of this make me think that the Fourier spectrum, Fourier-based spectrum, is not a very good spectrum. It does not give you the correct physics. Yeah.
Thank
yes.
you. And
most of the spectrum.
Another question is.
Yeah, just like for example, let me go back. This is peak. This is the harmonics. The water wave should be dispersive. Okay? But if you look at this frequency and also look at this frequency, that this wave and this wave actually propagate the same speed. So this wave is no longer dispersive. But it's in the same spectrum. So in the spectrum, your one wave that has all these harmonics are all spread over all kinds of frequency, but they are propagated the same velocity. So they totally violate this dispersive relationship. So these are not physical wave. These are bounded wave. These are the geometric shape to fit the sharp crest. Nothing but that. Okay. It does not have any dynamic significance at all. It does not follow the kinematics, does not follow the dynamics. Yeah. Oh, well, it follows the dynamics a little bit. Okay?
Okay. May I ask another question?
Sure.
Sorry, I came into the class a little late today. Maybe you already mentioned it, but I didn't hear it. The question is that it seems that the spectrum is very important What can spectrum tell us about the wave, the water wave?
Oh, the spectrum, if it's a good spectrum, it should tell the distribution of water wave as a function of frequency, the energy density at the different frequency. Yeah, and that is give you the statistical property of the of the water wave. Additionally, spectrum can be used to study like air-sea interaction, can study nonlinear mechanics, and can be applied to say like a marine structure design, yeah, ship design. That all depends upon the spectrum shape, yeah. Because the force, you try to calculate the force act upon your structure, and that depends upon the spectrum.
The reason I ask this question is that, for instance, when we use the spectrum of light, we can, for instance, if we collect the lights from other stars, right?
Yeah.
If we analyze the spectrum, we have some colorful graphs, so
right.
we can study, like for instance, the temperature of the star.
Yeah.
So do we have something analog to that?
No, the spectrum cannot give you a temperature of the water, but it can give you the wind velocity, roughly. Typically, the peak, the wind wave, the wave are generated by wind, and when the wind generates a wave, the velocity of the wind and the velocity of the wave should match, should be the same. So the wind can continuously pump energy into the wave, so-called resonance theory. So if you look at a spectrum peak, you should be able to get the mean wind of the generating wind. Yeah, but that has another caveat. For example, I can blow very strong wind. You look at a small body of water, and that wave will never match the local wind phase velocity. Yeah. So all of this has a you have to reach the mature state, then you can tell the wind condition. Yeah. Another thing that you can tell is, again, use the dispersive relationship. Actually, when I mentioned that the storm wave in the southern Indian Ocean can reach the coast of California, and people actually measured that in the 1950s. They measured the swell coming from coming into the California coast, and they find that the frequency keep changing. First you get a very low frequency, then you get a higher frequency, higher frequency, higher frequency. So this is precisely the dispersive relationship. From the rate of frequency change, you can deduce where the storm come from. Yeah, because you know the propagation velocity, you know if the generating area is very close to you, so the large wave and small wave probably arrive very close to the same time. But if it's get very, very far away, then the long wave will reach long before the short wave will reach you. Yeah. So you can use the dispersive relationship to study the arrival time of the wave, and from that you can deduce the generating area, and that was used by the script people. In the a few years ago, I used the same relationship, the dispersive relationship, the spectrum shape, in other words, to study the harbor sash. You know, a lot of harbor has this oscillation, inside harbor oscillation. And this harbor oscillation sometimes can be so severe. When a large sash comes in, it can empty all the water in a small harbor, and the little ship can be on the dry land. Yeah. In Puerto Rico, they have this internal sash that strangely, it come every month, every half month, it will come a big sash comes in. So they figure that where the sash come from, every month, every half a month, it has to be related to the moon. Okay, so the moon, the tide will generate that sash, and if it take a half month, 7 days to get here, so this sash must be very far. So they try to get this internal wave about 1,000 miles away. Yeah. So they all believe that, and tens of papers were written by by Chapman at the at Woods Hole. So finally, I get hold of the data from a friend of mine in NOAA, and I analyze the wave. I find that the wave frequency keeps shifting, and that means it's dispersive. And from the way that it dispersed, I deduced that the wave cannot propagate more than 8 hours. Yeah. So the wave, the sash actually was generated near Puerto Rico at the continental shelf. So all of that depends upon the dispersive relationship as well as the spectrum of the shape of the wave. That's what we can deduce. It's not like spectroscopy that you mentioned to deduce the material property, like different elements give you different atomic spectrum bandwidth, or we cannot do that. Yeah. But that Doppler shift, we can do a little bit Doppler shift, but it's not a whole lot. Yeah. You can deduce Doppler shift and get the maybe water velocity that the wave is riding on. Okay?
Okay. One more question.
Sure.
What kind of physical principle people apply when we design an instrument to measure the data that we need to get the spectrum?
Oh, there are all kinds of instruments. The simplest instrument is an elevation gauge. You have a wire. A wire penetrates the water surface. The wire can be capacitance, can be conductivity. As the water level change, then the capacitance or the conductivity change. The conducting probe usually consists of 2 wires. Yeah, capacitance probe is one probe with a probe. The inner probe, the probe serves as one plate. The water serves as another plate, and you have a shield in between that. So this is basically the principle in design, water contact probe. And other than that, you can use remote sensing technique. You can use laser, send a laser beam or send an acoustic sound beam to hit the surface and bounce back. You can measure water height that way too. Yeah, and in synthetic aperture radar, you can measure the water surface shape. And once you measure the water surface shape, you can using Fourier transformation to back out a directional wave spectrum. Yeah, that's probably give you the most complete wave spectrum shape that you can have. Yeah. Okay?
Thank you.
Any more questions? Yeah, go ahead.
After setting a global seismological observation station, the geologist found that the earthquake wave transferring in the crust material is also dispersive. So can this class topic use the same characteristic in the earthquake wave?
Well, of course, I didn't know. I thought that the sound wave is not dispersive, except the truly nonlinear sound wave. A typical earthquake wave, when you propagate far away, it becomes linear. It becomes non-dispersive. but it turns out it is dispersive. Well, that's fine. If you have that data, I have a very simple rule you can apply immediately. We can find out how far the wave has been propagating. Yeah, certainly. If it's dispersive, then it could be done. But then we have to know roughly the dispersive relationship, how frequency varies as a function of frequency, for example. Yeah, it can be done. That will be the same thing as I deduce the internal wave. Yeah, sure. Yeah.
What is the different dimension and scale?
Why it's important that the dimension has to be homogeneous, right? What's the difference between dimension and scale? Dimension is very different. Dimension, when I use dimension here, I use it more general, in a more general term. Dimension means dimension analysis means that I can dimension analysis. Dimensional analysis. Dimensional analysis, it's not what we call the dimension like the Euclidean space geometry, or one dimension is line, two dimensions surface, three dimensions is a body or whatever. It's not that dimension anymore. When we talk about dimension analysis, we'll talk about dimension like one dimension is time. Okay, time is one dimension. Space, length is another dimension. Okay, and if you have any other dimension, you can come up with a different dimension. And each variable has different dimension. Like velocity has L over T. Yeah, density is another dimension. Okay, mass is another dimension, and the acceleration is L over T squared. So this is the physical property of the variable. So in physics, in principle of mechanics, if two quantities are equal, the dimension cannot be different. In other words, I cannot say 1 second equal to 2 meters. It doesn't make sense. Any relationship doesn't make sense that way. Okay, 1 second equal to 1 meter divide 1 meter per second. It doesn't make sense. All the physical equations all have to be uniform dimension, like distance equal to time dot velocity, time times velocity. Time is t, velocity is L over t. T and t cancel, that's L. So time, velocity times time give you distance. Then time squared times acceleration. Time squared is t squared. Acceleration is L over t squared. So t squared cancel, you have L. So the distance equal to velocity and acceleration. But the dimension has to be uniform. Okay. Now to in the dimension analysis is a very powerful method. You analyze something too complicated for us to know. So you for example, you have certain variables like a spectrum. Spectrum should have a dimension of L squared times t. Okay. What the spectrum should be dictated by, or what physical parameter actually influence it. So you identify G, you identify frequency, you identify wind. Okay. But what it says is that there's a pi theory. The pi theory is whatever variable you have, but all this variable has its own dimension. Each maybe have L, may have T, or may have mass, or whatever. Here, the mass is not in here. Density is not in here. Density is mass divided by L cubed. Okay. So with this, then you deduce. You say, how many independent dimensions I have? T and L. So I have 2. Then you have 3 variables. Then we can deduce 1 constant. That's pi theory. Yeah, that's very powerful theory for us to explore the interrelationship among different physical parameter and variables. Yeah. Okay. All right. Any more questions? If you're interested, I can give you some reference. I have some reference you can read about. Okay. Yeah. All right. Well, if there's no more question, we have. I have stayed 20 more minutes after the Japanese sign off. I was told that our class is 100 minutes. The Japanese class is 90 minutes. Yeah. So we even stay beyond our class. Well, thank you very much. Yeah. We'll see you next week. Bye-bye.